I'm not naive enough to think lambda CDM is perfect truth that will last for all time, but empirically, it's a very accurate description of the universe we live in. We already know the vacuum energy, empirically, it doesn't alter its energy density by more than 5 to 10% over the last half of the universe's expansion. So we may one day get a more mature understanding of what dark energy, vacuum energy actually is, but empirically, as a description of the universe, we have so much data to say. This model has been around for 20 years, and the quantities of data that have been taken by new generations of telescopes just confirmed it better and better. So it's very like the standard model in particle physics from that point of view. If there are changes, there'll be, I think, minor variations rather than a great revolution. That's a prejudice. The other point I wanted to make is several speakers have referred to the concept of expanding space. And this is something where I wanted to issue a health warning. It's a term I hate. There's a Woody Allen movie, I forget which one, but where his mother tells him, oh, for God's sake, do your homework, you're in Brooklyn. Brooklyn is not expanding. Expanding space is a very dangerous term that can lead you to make severe conceptual errors. Space in this room is not expanding. And it's an anti-relativistic concept. What relativity tells us is everything is founded on the equivalence principle. A freely falling observer, or a freely falling galaxy, the experiences around them, the space-time of special relativity, Minkowski space-time. This does not expand. It's a meaningless concept in relativity. So Slipher in his early papers was quite correct to say that locally, interpretation of the redshifts or blue shifts of galaxies is entirely dogma. I think making a big mistake if you think about it any other way. Okay, that was. If we run out of things to talk about, I suggest we talk about those. So, having stolen a minute or so from the first speaker, for which I apologise, let's get on. He's very kindly given me a bio. So, Cormac O'Raifeartaigh is an experimental physicist at Waterford Institute of Technology in Ireland. He writes regularly on cosmology and particle physics in the media, and is the author of the science blog Antimatter. He's a former research fellow of the Science, Technology and Society program of Harvard University.
Okay, so hi everyone, can you hear me? That's great. First, let me start with a very abject apology to Robert Smith, who I see here, and also Helga Krach, who couldn't make it. Of course, forgot they have already used this as a title of a paper. And by the way, on the subject of homework, that should be the first thing. Compulsory homework for everyone. They have an excellent paper in the Journal History of Science with precisely that title, and it's extremely thorough. Luckily, what I'll be doing is something completely different, because it won't be thorough. Instead, this is a short talk, so I'm going to try and give basically a quick open bus tour. For me, I'm not a science historian, but I'm one of these scientists that I really believe that to truly understand something in science, it helps enormously to understand how we found out and how people examined it, and all blind animals as well. They're all important too. And so I see, I'm a scientist historian of science, if you like, in the sense that I look at the history of science with a view to understanding the universe, which is rather different than some historians. And I'm not talking about Robert here, but there's a new generation of historians who I worked with quite a bit last year at Harvard, where I feel they're historians first from the humanities, looking at science as a branch of history, which is quite a different thing actually. But anyway, let's keep going. Okay, so here we go. First thing I would say is there are actually, any of the Sliphers here, the amazing thing is his amazing discovery is really part of a sort of a triple whammy. It's really an astonishing period in science. We talk about the golden age of cosmology today, which is right, I think. But I mean, there were really three major discoveries around this time we're going to be talking about. One is, of course, the establishment that there were many galaxies. Redshifts played quite a role. I was delighted to hear Ken talk about that, because it's not always mentioned. The very fact that they seem to be moving at these velocities suggested that they weren't gravitationally bound. Of course, they played a key role in the next debate, which would be the debate of the expanding universe and the discovery of what went on there. In the context of relativity, that became the expanding universe, but the observation of the redshifts was, of course, a critical piece of information. And of course, what all that came later there was also highly related to the redshifts. Okay, now, what I'd like to say first, though, because this is usually left at the end of science talks, let's start with it. On the nature of discovery, of course, there's a problem with this word. It's surprisingly hard to pin down what we actually mean by the word discovery. A lot of the time we say discovery when we mean observation, for example. I would say Penzias and Wilson detected the cosmic microwave background, or observed it. I'm not sure I would say they discovered it, because to me discovered kind of involves an understanding of it with some sort of an explanation of etc., etc. And for that reason, many people would say Hubble didn't discover the expanding universe. We'll come back to that. On the other hand, there's the thing of hypothesis. So I enjoyed Greg's talk, but for example, in the Copernican model, you could say Copernicus made a hypothesis. A theoretician would say, hang on, Kepler was the one with the elliptical orbits, which were based on the observations of de Broglie. And then you could say, well, hang on, Newton gave the explanation in terms of gravity. So at which stage does that discovery actually happen? And a lot of the confusion, I think, if you can call it confusion, is about what do we mean by theory versus experiment. But anyway, that's one thing. Another thing I'm extremely interested in is what philosophers call the context of justification, as opposed to the context of discovery. I'm actually not that interested in who discovered what at any precise moment in time. I'm much more interested in what happens next, because I myself have made many discoveries. The reason you've never heard of me is because they haven't been justified. That's the thing. It's what happens next, and especially if there are multiple lines of evidence showing that this discovery or this observation is on the right track. That's a very, very important point. But if you think about it, it means that nearly always our view of science is retrospective. When we celebrate somebody, it has to be retrospective, because it's only on the basis of what happens since that we realize it's important. It's very, very rare that people instantly realize it's important, etc., as Ken pointed out. I'm also extremely interested in this thing of rediscovery. I think it's absolutely fascinating that, whether it's Lemaitre and Friedmann and then Lemaitre and then Robertson, for example, or other examples throughout science where things are discovered independently in different places. Now that to me is a very clear message that there's a real world out there, and very often science progresses to a certain extent that the next discovery is, in a sense, it's almost inevitable. That's not quite the right word, but you know what I mean. It's going to happen, whether they know about each other or not. It probably happens less nowadays because of the communication, etc. But it's really interesting to see that, and it confirms my belief that what's really important here is the importance of scientific context. I don't buy into at all the modern obsession with the importance of social context. In fact, I would say it's unimportant, completely unimportant. In the long run, I don't care what job they were running for or what they were doing when they measured something. Because if you think about it in terms of the justification, it doesn't really matter in the long run. It matters at that point in time, possibly, though people often speculate about things that I don't like speculation. You can't be sure somebody did this for a particular reason. Even if they wrote it themselves, you can't be sure. Anyway, so, oops. In terms of, I like to start the story with the nebulae, just 1 or 2 slides on it. Of course, they were observed in Europe, at least, way back in 1614 by Simon Marius, and then by people like Halley and Messier. The word island universes is associated with Kant and Laplace, and I enjoyed this morning's talk. I have no idea whether they used it or not, and I accept your word that they didn't, but let's say it became the jargon and we associated with them. But the big question was, were they a collection of stars at immense distance? In other words, are we in the Milky Way looking out, and there are other collections just like that, which is a wonderful idea. But the real reason I think people got very interested was, of course, the idea that maybe stars are born in the nebulae. And then, telescopes got a lot bigger. Wilhelm Herschel came along, built his 36 reflecting-inch telescope. A guy who very rarely gets mentioned is the Irish aristocrat, Earl of Ross, who specifically built, his hapless tenants built this 72-inch reflective telescope, whose job it was to try and resolve these nebulae. And sure enough, he was able to show that some nebulae have a spiral structure, and indeed he was able to resolve some stars. Now, he never said all nebulae were like that. He was a careful scientist. He said that maybe more than one type of nebulae, but some of them have a spiral structure. But of course, the real problem here is no one had any idea how far away they were. Then we come to the hero of the day. It was at Lowell's suggestions, as we heard today, that Slipher made these measurements. I would say his genius, in a way, he's the opposite of Burke-Castle. He realizes it's not about, to measure the spectra, it's not about huge telescopes. It's about camera speed, exposure time, etc. So this is a whole new branch of astronomy in a way. It started by William Huggins, you might say, but it's certainly perfected in terms of spectrograph by Slipher. And the first thing he mentioned in 1912 that we need is that basically that he saw these Doppler shifts, interpreted them as a radial velocity, delta land over land is v over c, approaching at a very rapid speed. And by about 1915, 1917, so on, different publications, he had quite a number of these spiral nebulae. Most of them seem to be redshifted, and some were even receding at speeds of 1,000 kilometers per second. And as Harry said, what's important about that is it's easily 10 times faster than the known speed of local stars. And it raised the question, well, were they gravitationally bound? Were they within the Milky Way at all? Another heroine who didn't get mentioned yet, so I really have to mention her, is Henrietta Leavitt. This wonderful relation. How do you measure distance? At last, shows that there's a relation between the period of a star and its luminosity. From that, you can work out the intrinsic or the absolute luminosity of the star, and from that, by looking at comparing that with the apparent luminosity, you can then calculate distance. So at last, we have a standard candle for things which are very, very far away, provided you can find the CV variables. So, I mean, I'll just point this out. You know, it's a moment in time, but let's say the great debate has been dragging on for about 400 years, really, at this stage. But you know, I think it's asymmetric at this stage. Most people are convinced by three things: the stellar structure of the spiral nebulae, the fact that these redshifts seem to be around. We didn't mention novae today yet, but this idea that there are quite a few novae around, and they seem to be, first of all, they're very rare, and yet they seem to measure quite a few of them. Also, they were 10 times fainter than most, so that suggests that they were a long way away. So that all gave support to the distinct galaxies, and we associate that with Hale of Curtis. Shapley, I think, was quite unlucky in many ways. He was sticking to his big galaxy model because he had used what he thought was CV variables to measure the size of the Milky Way. They weren't, but he wasn't to know that. Also, he relied heavily on some rotation data by Van Manen that turned out to be wrong. But also, again, he really was unlucky. He relied heavily on a nova in the Andromeda Nebula, which turned out, of course, nowadays we know to be supernova. So you know, he was a very, very good experimentalist. It's just he happened to be on the wrong side of this particular debate. Okay, and so a clear resolution comes along, not from a person, if you ask me, but from an instrument. The Hooker telescope was built, well, let's say went into operation in 1917, 100-inch reflector, so that's bigger again than the Earth-Glasses telescope. And you could argue that we had the right man in the right place because a young, highly talented, but highly ambitious astronomer goes to work on it. And between the years 1923 to 25, he resolves Cepheid stars in several nebulae by applying the Levitt law, Levitt's law, Shapley's calculation of Levitt's law. He establishes that these nebulae are at extremely large distances, even bigger than Shapley's calculations of the size. So that is one of those moments where I think, do I have a slide out? Yeah, you could say, in terms of the discovery of the galaxies, it's pretty quickly accepted, and it's exactly as I think Harry made the point earlier, that you know, the idea had been around for a long time, so it's not that surprising that once the evidence is there, people can get back to it. I don't agree for a second, and won't be time to talk about it today. It's what people call a Kuhn paradigm shift, and from then on, no other possibility was possible, blah, blah, blah. No, I think that's just the way the evidence pointed. It's a slow accumulation of evidence over a very long time. But anyway, for our purposes, we're exactly true. For our purposes, the real question then was, okay, well, if these spiral nebulae are galaxies, well, now we really want to know what those redshifts represent. It wasn't clear, it was always a question, but now it's really, because once you've established that they are galaxies outside of the Milky Way, suddenly that becomes a very interesting question. But the reason I have the four people, I call this person, Hooker telescope, Hubble, Levitt, and Slipher, all of them contributed. All of them made important, so it's okay, so now here we have the question, of course. For many, I'm presenting this as astronomers. At this point, the narrative changes because the astronomers start wondering, well, okay, what do those redshifts represent? If they're really recession velocities, why would the galaxies be rushing out? Newtonian gravity pulls in, it's the only force we know of at these sort of scales. So what on earth would be pushing them out? That's the question. And of course, at this point, somebody become aware that this theory has been around since 1915. Einstein's hypothesis that, first of all, space and time form one entity, which is space-time. Space-time is dynamic. It can be distorted by motion, it's a special theory, or it can be distorted by mass. And then, of course, that distortion causes other mass to move. And there's a famous equation, it's the simplest possible, let's say, combination, that the geometry on the left-hand side is equal to this constant times the mass-energy tensor on the right-hand side. And already by 1919, there was, shall we say, tentative evidence. We're going to hear a great lecture tomorrow, I think, by Peter Coles on this, but already tentative measurements had emerged to show that this might be right, which had turned Einstein into an overnight slide. Anyway, at this point, and this is the only difficult slide, at this point Einstein applies it to the entire universe. The most important point here, by the way, is, and everyone forgets it, Einstein himself points out in the paper, this is an extrapolation. There is no evidence whatsoever that general relativity does apply to the scale of the whole universe. Nobody knows that. But if it does, this is what you get. So assuming the cosmological principle, which for any of you who don't know is that the universe at the larger scale is isotropic, homogeneous, what he gets is a dynamic universe. Now, Einstein does write to a few people, we even have the letters. He asks a few people, is there any evidence for such a universe? He's in Europe, he doesn't ask the right people, if you like, or and this is quite early on anyway, but nobody has heard of such a thing. He gets that look he always gets when he asks people crazy questions, and so he adds in his cosmological constant to keep the universe static. And then he ends up with a universe which has a finite radius, which is extremely exciting. He can now calculate the radius of the universe, he can calculate the mass of the universe, and it's a universe of close curvature. And the equation looks like this. The geometry term now has an extra little term added in. First couple of remarks on that. First, it is not a fudge factor. For those of you who went to school, you would have heard of the constant of integration. It's the same idea. It could be there in equations all along. There's no reason to assume it's zero. It has to be very small, that said. Why? Because boundary conditions are set by the motion of the planets. So it has to be small. It doesn't have to be zero. So it's not, it's not a fudge factor at all. Secondly, as you all know, Einstein later describes it in beautiful language as my greatest blunder. We all has this image of the world's greatest scientist blundering around in a room. But anyway, it's not. The blunder is, as you all probably know, Lemaitre shows later, actually that constant can't keep the universe static. So it's a mathematical blunder anyway. Anyway, to continue on, you've all heard of the deserted universe. I'll just remind you, he considers another case. Let's take the simplest universe of all, with nothing in it at all. Apply the theory, he ends up with something that's apparently static because of the coordinate system he chooses, and it predicts redshifts. Two types of redshifts. One, if you put in matter, it runs away from the observer. The other, due to a time dilation effect. That immediately attracts quite a lot of attention. First of all, actually, I think Harry's right, it goes the other way, it really doesn't. De Sitter notices that there's a strong astronomical evidence. He notices Slipher's results, and Slipher's results and promotes them as evidence for this model, but it works both ways. I think a lot of people become interested in this prediction. And so here come what I call the heroes, because they tried so very, very hard. Anyone in the room who believes scientists measure what they expect to measure should read these papers and read them carefully. Here they are very carefully trying to take this amazing new theory and applying it to what is measured, and of course they fail. And the reason they fail is exactly what John was talking about, because actually it's an expansion of metric. It's a metric thing, it's not an expansion of Euclid scales. But anyway, they all look for this. I won't go through it because you've heard all about it. But I mean, look at Lemaitre, that's even the title of the paper, Determination of the Curvature of Space-Time. But what hope does he have? He's looking at stars and global clusters. It's easy for us to go back and say, well, of course that's not going to look. So instead here comes my hero, Friedmann universe. Friedmann instead shows there are general solutions to these, general solution, time-varying radius, where the universe is expanding or contracting as an expansion of metric. So three possible curvatures set together. I just want to quickly mention what I love about this is, first of all, he's got periodic solutions which correspond to the modeling of the cyclic universe. Secondly, these are entirely hypothetical models, not because he's not interested in physics, in the physical world, but because he feels it needs to be decided later by astronomy. In other words, he's looking at all possible universes, and that's a perfectly valid thing, that's a very good one. But Einstein doesn't like it. First he thinks it's made a technical error, and then he describes it as suspicious. Then we have Lemaitre. Now we've heard lots of them, so I'll just bring to this. The thing about Lemaitre is he comes up, first of all he shows the famous De Sitter model is in fact an expanding model, 10 years later. Matter-filled universe of increasing radius is the famous paper in 1927, but crucially he makes the connection with astronomy. He shows that suggests that the redshifts that have been measured by Slipher are in fact, well, we have, sorry John, I have the expansion of space, but an expansion of metric, let's say. And the rate of expansion can actually be calculated. He takes an average measurement from Hubble's measurements in 1925 and 1926, combines it with Slipher's measurements, and gets a value like that for the Hubble constant. It's put in what we call an obscure journal. He probably considered a perfectly reasonable Belgian journal. But anyway, it was rejected by Einstein, A, because he didn't believe it, and B, he said, don't you know some Russian guy came up with this a few years ago? That must have been quite crushing. Anyway, Weil's principle came out at this time, so did Robson. Lots of people are coming up with this. So, nearly there anyway. And then comes the clincher, Hubble and the redshifts. I think he would have been very interested in this, all right. Partly it's a natural next step for the guy who's established how far away the nebulae are. This is the next step, not for theoretical reasons, but very possibly, and this is my own speculation, because it would provide a new way of measuring distance, I would have thought. Anyway, he combines it with Slipher's measurements. Unfortunately, he gets this lovely line, but unfortunately, he doesn't quote Slipher at all, as we all know, which is disgraceful, and he gets an approximately linear relation, an empirical relation. And so it's at this point, this is fairly rapidly accepted even before the next set of measurements, and Eddington makes his famous remarks, coming up now to the end. Lemaitre then makes his intervention, says, do you mind, I sent you that paper in 1927, and Eddington and De Sitter very quickly become convinced of it, and the theory is translated. I won't go into the fake controversy that came came out of there. But let's just say at this point, there is now a Hubble graph and an explanation. The astronomers, however, are skeptical, and they do exactly what experiments should do, is that they keep measuring. And this is the graph that should know it. So I'm so pleased to see how they show this, because this is, you know, in terms of justification, it's what happens next. Now you can see it's linear because of the reduced scatter. These measurements have been made by Humason, some really great experimental physics going on there, and now it's clear there is an empirical relation. They don't draw any conclusions. They feel theory should be left to the theorist, which I think is perfectly reasonable. And so, okay, and probably, let's say very quickly, Lemaitre gets shafted a second time, because immediately Einstein and de Sitter then meet and put together a new universe. Einstein is delighted now to get rid of his cosmological constant, not just sets it to zero, but gets rid of it altogether, and talks about a universe of critical mass density and flat geometry. And that becomes the standard model, despite problems of age and problems of matter density. And I just can never resist showing this picture before I show the summary. Lemaitre, on the other hand, comes up with a model in 1934 that looks eerily like what we talk about today. He has a positive cosmological constant. He's talking about an accelerated expansion. Of course, this is mixed in with the next big step, which is he's talking about a universe that starts as an expansion from radioactive decay, the famous primeval atom. And the stagnation period takes care of this age problem. But I don't think it's fair, and people keep saying it today in this conference, that he brings in the cosmological constant to get rid of the age problem. No, it's clear from Lemaitre's writing. He has always thought as the cosmological constant as a very, very important part of the relativistic equations. Not only that, but in this instance, right back in 1934, he starts talking about it in terms of an energy of vacuum, and even gives an equation for that, which is absolutely astonishing. Finally, I can't resist, like Friedmann, he also talks about a cyclic universe. So, you know, history, maybe history doesn't repeat itself, but it's certainly rhymes. Isn't that astonishing? He's looking right there about a cyclic universe. Now, so to finish with, if you were to ask the question, who discovered the expanding universe, I would say all of them. That's an easy question, all of them. But of course, if it was like the Olympics or something, and you're in the business of awarding medals, a lot of you would say, well, Lemaitre first put together theory and experiment. My father, who one or two of you might know, was a very, very famous physicist. I'm just a very normal experimentalist, but it's funny being the son of a theoretician. He was a very good theoretician. My dad would have said, no, Friedmann does exactly what theoreticians should do. He develops the most general solutions. He's not talking about our universe, he's talking about all possible solutions. And he would argue that you could just as easily give the first medal to Friedmann. On the other hand, and I disagree very slightly with some people on this, I think there is an argument for saying a Hubble-Slipher law in terms of empirical law. Science is full of empirical laws. Ohm's law, lots of laws like that. On the other hand, it's true you say Einstein's law of the photoelectric effect, which is a predictive law. So we seem to change our minds. But you know, I could live with the Hubble-Slipher law, and I'll tell you why. Because these guys are immortalized anyway. So there's a nice point to finish on. These are immortal. Any of you who have actually, you know, opened a book on cosmology, you will see Friedmann Lemaitre models mentioned on every page. You'll see the FLRW metric, Walker-Robinson, on every second page, etc., etc. So they are immortalized in exactly the way I think they would have loved that. You know, they're immortalized among their peers, which is what would have meant most to them. In terms of Slipher, though, he doesn't get that. I should have mentioned there as well, I think Henrietta Leavitt is in the same category, and it is terrible. And let me finish by saying, though, it's really the discovery that's important to me, not who discovered. And I would strongly argue that it's to do with a slow accumulation of theory and evidence. An idea that comes into its time, not an idea of its time, the opposite. An idea that is there that comes into its time is the way I think of it.
Good, thank you. We have time for some questions. Right.
Yeah, I noticed the early velocity distance data were the earliest ones that we've seen, were all over the place. Then you saw Hubble's looks more linear, and the Humason one also was very, how come it got so much better?
I suppose, well, two reasons. First one is that I should have said, of course, this is 18 times the distance scale, so they've gone out much, much, much further. That does make a difference if you think about it. Secondly, they've improved, if I remember this right, there was a lot of problems with peculiar motions with some of them. and they made progress between then and there. But
I'll talk about that tomorrow.
Okay.
It's also worth pointing out that each of these points is the average over a substantial number of galaxies.
I forgot to say that the first one is not right. They are each one of these is an average.
Yeah.
Whereas on the first slide, a lot of them are
Another
actually
question
different.
I would take issue with your characterization of Kuhn and what constitutes revolution. It's not probably important since it deals with historical issues, but I would say that it's in response to a crisis. And if we're meeting today and don't recognize that there was a crisis, I'm very surprised.
I'm so glad you asked that. There wasn't time, but no, my issue with Kuhn isn't the whole business of revolutions. My issue is two statements which he makes very clearly in that book, which we'll be hearing all about this year because it's the anniversary. One of them is when the revolution happens, it happens as much for social reasons as for science. And he did say that. People keep backtracking and saying, yes, he did. It's quite clear, and he also wrote papers on it afterwards. I don't accept that. I don't think it is accepted for social reasons. I think things get accepted because that's the way the data points. But even worse, he makes a third thing. There's a revolution, says acceptance. He makes the point that when the paradigm shift has happened, it is then incommensurate with the model that was before. Now, if you go into Trinity College Dublin as a first-year postgrad, you will be kicked out in a week if you have an idea. When you make your measurements as an experimentalist, you have to compare those measurements with every possible model. The idea that you can't compare it with some model over there because it's no longer fashionable, maybe that's true in some areas of human activity. That is not true in science. I simply don't believe that. And his evidence for that is incredibly flimsy. But unfortunately, and can I just finish the question with this? I don't think Kuhn is that bad. But yeah, unfortunately, he then gave rise to a whole movement of guys who took him to extremes. There's, I am not a Kuhnian, is what Kuhn says. Practically on his deathbed, because he gives birth to this incredible, this whole thing of the science studies and sociology of science by people who go to all sorts of extremes. But we can talk about it.
Carl.
Can you expand upon your point about Lemaitre calculation of the vacuum energy?
Say that again? Yeah.
Can you get a number for that?
Do you mean where he gets the idea? Does he give an actual figure for it?
Yeah. You notice the number was not rather large.
That's a very good question.
Well, they had a Hubble constant.
What is
They were
lambda?
assuming that the vacuum energy dominated.
No. Well, you say you actually calculate the vacuum energy from quantum physics, or
No, he just took the rate of expansion as inferred from data and assumed
So,
vacuum
place a limit on it.
Yes, but he does mention it in a qualitative way. He mentions it in the context of the quantum energy of vacuum, but he certainly doesn't do the calculation of thinking.
Well, they're known by that time, 1916, I think, had done the first quantum calculation. That last one.
Oh, just very quickly, you can actually encapsulate your entire first slide where you go through all the difficulties and such of the scientific method, and your statement that the people who think it's all a social construct, that's all can be encapsulated in a single statement saying that scientific method works, but it works on an intermediate asymptotic manner, right? It doesn't work on the time scale and size scale of one particular scientist and one particular
I think that's
career, but it's more complicated, just as you've said, but you can encapsulate it in that one.
I see what you're saying. You're saying that
And that's exactly where all the critics, the Kuhnians
I
and
think
the
you're right.
Friedmanns and stuff go wrong, is all of their criticisms make that wrong assumption that it all has to happen on the scale of one guy.
That's good.
It's usually a guy too, but that's a separate
And do
issue.
you mean they're always looking at one point in time, whereas the integral over the time?
Yes.
That's the
It's the
that's great.
it's
I
the
never need to
intermediate
articulate that.
asymptotics that they're missing, right?
Yeah, that's exactly right.
Okay, Cormac, thank you.